As a kid, I remember being amazed that water bugs were able to do something as magical as walking on water. A water bug is able to stay afloat on top of a stream due to the high surface tension of the water. Surface tension is defined as the molecules at a liquid surface exhibiting stronger attractive forces compared to the attraction between the molecules below the surface. A water bug can stay afloat because its weight is small compared to the area of its feet. Hence, the net force from surface tension is able to achieve static equilibrium with the net weight force. It uses all 6 of its legs to distribute its weight evenly on the surface and uses hydrophobic hairs to avoid breaking the surface tension. The following calculations and analysis provide numerical evidence for how the water bug stays afloat.
In order to complete our calculations, we first made a few assumptions. We assumed that the bug had 6 equal weight and equal length feet. We also assumed the weight of the bug was distributed equally to each foot. We made the simplifying assumption that the maximum surface tension occurs when exactly half of each leg is submerged, or when theta is equal to 0 and cosine is equal to 1. Our first calculation was the average weight of a water bug. We found that the average mass of a water bug was 0.25 grams. Since weight is equal to mass times the gravitational acceleration, after solving, we found that the average weight of a water bug is 0.00245 newtons. This is the force acting downward on the bug as seen in our free body diagram. We then found the maximum possible weight of a water bug from the maximum force of surface tension. The surface tension of water, or gamma, is equal to 0.073 newtons per meter. The length of each foot of a water bug is 4 millimeters, and as stated previously, the bug has 6 legs. The force from surface tension is equal to gamma times the length of the surface in contact with the water. Therefore, our equation was equal to the number of legs times gamma times the length of each foot times the cosine of theta. We multiplied this formula by 2 since there is a force acting on both sides of the leg. After calculating, we found that this value was 0.003504 newtons. This corresponds to the maximum allowable weight of the water bug, since any force greater than this could not be counteracted by the surface tension force. Because our value for the average weight of a water bug was less than this maximum allowable weight force, this means that our bug will be able to stay afloat due to surface tension. For some further analysis, we calculated the angle theta for our average water bug. This angle was found to be 45.6 degrees and would correspond to a state in which the bug's leg was not half submerged and would be less submerged. If the bug weighed any more, its leg would become more submerged because the surface tension would not be able to combat this force and the bug would start to sink.
In conclusion, in order to determine how a water bug stays afloat on the surface of a stream, we set up a free body diagram to analyze the forces on the bug. After calculating each force, it was found that the surface tension can exert more than the force required to keep the bug on top of the water. This surface tension is due to relatively stronger intermolecular forces at the surface compared to below the surface. A water bug can float up to a maximum weight that, if surpassed, will break the surface tension, disrupt the static equilibrium, and cause a net downward force and acceleration.